there is something else after that. So maybe around 30 minutes I'll try to wind up, and I'm trying to cover something which is our host Dr. Sonal asked me to do so. May not be direct from my research areas. I have been working on biochar from the day of my PhD. That time I was just mentioning Sonal and all that a few minutes before that. This biochar terminology has been coined since last few years. Okay. Earlier people used to talk about activated carbon, so my thesis is on activated carbon, and of course a reactor development in which we have used that activated carbon for wastewater treatment. Now anything that comes from a biological sources, you put bio before that, so basically it's the activated carbon, right? And more than that, I think I'll not go into detail about the biochars and all, because I think today is the fourth day. Many speakers have covered many aspects of biochar. I will stick to some of the things which I feel that either we are doing or is very important from the perspective of today's biochar market. So this is for my friends from France. As you know, IIT, we have 23 IITs, okay, and I don't know whether this works. So this is from the place where I come. This is Assam, and this entire cluster is called the Northeast states, having 7 sister states, and of course Sikkim is there. People don't so put it for some different reasons. And this is from where I come, Guwahati. And Dispur is the capital of Assam, and we are now situated here in Roorkee. And we started at 1994 after almost the sixth IIT, you can say, after the 5 first, almost at a gap of 35 to 40 years. There were no more IITs. Now then we have 23 IITs. Correct. Anyway, so just to say to my friends that from where I come, let me begin. So, if you look at biochar market in Asia Pacific, there is a huge demand of biochar, and you can see China, Japan, South Korea, India, and the rest of the Asia Pacific countries. And what I have observed in one of my visit to Seoul in South Korea is this: probably you will be knowing that South Korea is world's leading manufacturer of cosmetics. Correct. So for all such of cosmetic applications, whether it is a face pack, even nowadays biochar in the toothpaste, okay, that we also have here, right? So for all such applications which has a intended use for the humans, we have to use char or biochar which is benign in nature. I cannot use a biochar which is been activated using zinc chloride or any such chemical activating agent. Either it is physically activated or it has been derived with a source or in a process which is very green. So in this particular aspect, I would like to say that hydrothermal carbonization using water as the benign solvent is an excellent tool to produce this so-called benign hydrochars or benign biochars for these cosmetic applications. Now let's move on. So if we stand at year 2024, even as the data says that the market is almost $272 US million dollars, and it is growing at a rate of almost 12 to 13%, and will grow and reach around 633 USD millions in by 2032. So what is the intention of showing this particular graph? This is projected market, right? It may vary, as you know that it always varies. It may be more than that, right? Because if you look at closely India, Indians will understand, India is a huge market for anything, right? We have almost 140 crore people here, and this is a big country, huge population. So anything you know, so one of the best understanding of how Indian market is the adaptation of the mobiles, cellular technology. Okay, anybody is having a mobile now. It's not about a mobile, it's about the type of mobile people used to prefer. Okay, the smartphones basically. So we have an excellent market in India, we know that, and there are excellent reports which implies even by DST also, one of our prime funding agency, which has also carried out a Biochar mission, and combined with the National Bamboo Mission also they have done some work. I was part of that group for some discussion, and I have also closely noticed that India has a huge, India is a huge biochar market. So of course we need to tap it. So coming directly to different types of precursors, or let us say the materials that we use for preparing biomass. So lignocellulosic biomass stands out because of its inherent nature, that it has having the lignin, cellulose and hemicellulose, plus there are many other things. And if you have more lignin, you are going to go, get more char. It's so simple, right? And but in India, if you look at this particular data, this is the surplus crop residue which may be used for the biochar production. It's not that it is meant for biochar production, but we can always use it. The UP, Uttar Pradesh tops the list. Okay, and India is an agricultural driven country, or driven economy you can say. So we have huge amount of agricultural residues that's been generated every year, and that's not being used to its full potential. So again, we also can tap the potential of such wastes to produce biochar and for different end users. By having said that, one thing you must not now be understanding in this last 3 to 4 days of this particular symposium, that I just cannot take any biochar and produce it from. I just cannot take any material and produce a biochar. So always the intention of a particular biochar, how I am making, how I am going to fine tune it, should always be focused with respect to a particular application. So now one particular char can have a multiple application, that's perfectly fine. But always we can make tailor-made biochars. I want to wastewater treatment, I have a different biochar, correct. The features I can tailor it. I want it as a catalyst, I need to impregnate it with metals and all. So and so on. So if you talk about one of the most interesting biomass that we are blessed with in our entire northeast is bamboo. Okay. Now, Government of India has a National Bamboo Mission. They do a lot of policy making, that how bamboo can be utilized. One of its finest utilization is to produce alcohol, ethanol, bioethanol. Okay. Because Government of India has mandated 20% ethanol blending now, but we don't produce so much of ethanol. Okay, so I'm happy to say that from my place only, from Assam, the Numaligarh Refinery Limited is this year commissioning a very big bioethanol plant completely running on bamboo. Now, there are so many different types of bamboos. Okay, the bamboo which we are going to use, and I'm part of that NRL activity. It's with the Swedish collaboration, and is that we have n number of varieties of soft bamboos, okay, and very fast growing bamboos. Now, if you say that I will be producing large scale ethanol from bamboo, then I need to have a huge supply chain system that is working, right? And any biomass, it's all dependent upon the environmental climatic conditions for its growth, soil conditions, water availability, and plus so many other things. We will not get into such things. Now, bamboo has been found to be one of the best precursor material for biochar production for various applications. So we also do, in my group also, we will do a lot of work on that. Just in the end of my presentation, I will show you a few things that we are doing in a quick graphs. This slide is to make you understand that in India, if you talk about bamboo, we have huge potential to use it. earlier days we used to use as a construction material. Now, except in few villages, we don't do that. Okay, so the entire amount of bamboo goes for other, mostly char making, and of course going into our ethanol plant. Now, I think this has been covered by many of the speakers. What I want to show, this is part of one review paper that we recently published in Stockton, is that if you let's closely look at this. So you see, you produce char by different methods. Okay. Then let us say you eliminate it. So we can have different types of applications like some pollutant removal and exhaustion of gaseous components. So you can have a biochar, either activated it or we don't activate it. It's not that you always activate it. Okay. Again, you can tailor make it. I just mentioned that for a particular application. Now, we have n number of applications. I think many of earlier speakers might have covered. I'll just quickly go through some of those. As I mentioned, that one of the technology in which I am very much interested, okay, is this hydrothermal carbonization. There are two things we call hydrothermal carbonization because I am making char. If I am making liquid, I call it hydrothermal liquefaction, and that's what we do to produce crudes from various biomass and some platform chemicals also. Right. So as we know, that due to its inherent nature, whatever is mentioned here, I'm not reading it again, that the most important thing is of course the excellent porous structure and then high surface area. Again, all these two properties also you can tailor make it, right? By choosing a proper activating agent, and of course we can also go through physical activation. So, what is the main important aspect of the biochar market right now? If you look very closely, see the water purification system. Okay, there is always a activated carbon column. Now, due to the stricter guidelines, because this is for potable water, again you are not supposed to use the char which is big chemically activated. So because this is for potable water, drinking purposes, so there is a huge demand suddenly last 15 to 20 years or something like that, is that we need a huge amount of the char which is again not chemically activated for this particular application. This is only one application, water purification. Now then we have n number of applications. So let me start now giving some basic essence of different types of applications of the biochar. So one of the foremost important applications in which we work is the biochar as a catalyst. Okay. Now we can have different types of biomass. We can have different types of conversion process, maybe torrefaction, pyrolysis, gasification, which are the thermochemical conversion processes. We can have conventional processes, of course, using hydrothermal also, microwave also. Then either you do activation physically or chemically, or you go by some modification. But what I mean modification is that I am impregnating some additional thing on the biochar. That's how the catalyst is. So I work on bifunctional catalyst. So in which we use biochar, we prepare biochar from some biomass, then impregnate with some of the metals which for a particular intended application. Correct. So this my particular work I show you at the last. And when you talk about biochar in catalyst, so we can have photocatalytic system, we can have oxidation reduction system, so we can have sonocatalytic and Fenton-like system. So every such process, all the four mentioned here, are for mostly the wastewater treatment, and they all need a catalyst. Correct. Now earlier people used to do the commercial catalysts, which are obviously very costly, and due to the inherent price that is associated with the commercial catalyst, the price of your treatment goes on. So always there is an issue with the price versus the amount you are actually treating, whether it is water, gas, whatever it is. So the focus is again how to develop a low cost catalyst. from different types of materials. So when you say materials, obviously the biomass comes into mind. Again, biomass means you are not supposed to cut the woods, trees and all such things. So you are you have to rely on materials which are actually coming as a waste product, or let us say the byproducts, like this crop residues, forest dwindling, and number of things are there. So we call them engineered biochar, right? So the engineered biochar with high porosity, surface area, and active functional groups, okay, are more prone towards facilitating the electron transfer as well as catalytic reaction for the biofuel business. So I work on biofuels. So whatever we do with biochar is actually for that either environmental remediation or for the biofuel products. So again, on that particular work what we did, I'll present you in the last. So let us move on to the biochar in batteries and electrodes. So I have been recently started working. It's not my particular research area that I have been doing last 15-20 years. No, just started when my PhD student has joined. So he told me, sir, I wanted to do something like this. I told fine. So now I have to read also. So because this is something new for me, right? And so I am basically a chemical engineer and having expertise in environmental and energy applications and biofuels. So this is something new, but anyway, interesting. And what I always try to do is that when I was mentioning Sonal that I had to read a lot, because you mentioned me about that you have to speak on batteries, supercapacitors, I thought fine. So no issue. So batteries is nothing new, right? Batteries were there in 200 BC also, and they are a sustainable source of energy. And what is the problem in battery is that anyway, the cost is obviously the high, energy density and all such things are always an issue, right? Including that of your lithium ion batteries, okay, because it's very costly. So slowly people have started thinking that how do we develop batteries, or let's say supercapacitors, in an extension version of the battery only, and to make it more efficient as well as less costly. So that's the idea. So based on that, again, in the battery also the biochar has come into picture. That whether we can replace it, so the graphite came into picture, not now, since long. So graphite has been used in battery supercapacitors for a long time. Again, you know graphite is very costly, correct? So people have started replacing graphite with biochar. So there are a lot of interesting works. I'll try to say one or two which I read. Okay, that's why I put it in the PPT so that otherwise means I cannot justify. So another interesting application of biochar is in the MFCs, the microbial fuel cells, in which we did also some work. We actually work with plant-based microbial fuel cells. Okay. So the plant is growing and then it's a microbial system with some organic things, and we have designed a novel PFMC in which the plant is growing. The plants which are basically essentially good for the air, purifying air inside rooms like this, okay. And then it will also generate some sort of electricity. You can store it using small entities. That it can charge my mobile or sometimes laptop. So that's what we have developed in our lab. Anyway, I'm not going to show you in all these things. So electrodes in battery systems must have high conductivity, and it should be a good corrosion resistant material as well as having stability. Okay. Now stability is an issue, you know that in sodium batteries, right? And for microbial fuel cells, especially microbial fuel cells, cathodes have a higher impact on performance, because they must have the higher oxidation reduction potential to support the capturing of the electrons. Otherwise, what will happen? The electrons that are being coming from the anode, it will not be captured. So that cycle will not complete. So it's not that cathode anode is the only important because that's the emitting zone of the electrons. No. That other part is also important. So when the business of biochar started in battery supercapacitors in MFC, people have started developing anodic cathodes using biochar, but of course there are cathodic things are also available. So let's move on. There is an interesting one by Nastro et al. I have given that reference later below. You can see. So what they did, they did compare the PTFE, okay, composite battery, cathode, and then another one, they have reduced the PTFE and they have put biochar in different proportions. Now these are from literature, I cannot show you all the data. The idea, I'm not showing any data in my presentation except that few will see for my own research, is that you need to, I need to give you an overview that how it is happening and where we are moving in the entire biochar business. So what is interesting, they have used vegetable threads using Pseudomonas aeruginosa in the microbial fuel cell. So what they have noticed that PTFE cathode is always resulted in a higher current output. It will, because it's in the purest form. So the moment you add biochar, its performance is reduced, but there is a catch. So go to the third line, you can see here. So the PTFE cathode fuel fouled very quickly. Correct. So that's the biggest problem with having a PTFE or let us say that this type of materials used as a cathodic material. So in when they compare it with a biochar based cathode, they found that biochar based cathode was successfully used for the 3 cycles, and every cycle spent for 15 days. Okay, so 45 days of uninterrupted non-fouling microbial fuel cell performance. Whereas in the case of only PTFE, within 10 days it's gone. It's gone in the sense that it fouled. You have to then remove the fouling using some mechanical method. And it's all, everything is not about the current input or density and all such things. You need to look for the other aspects also. Sometimes the environmental aspects, sometimes the stability issues, sometimes the operational issues. Correct. Now there is another work by this group called Mohanty et al. Okay, the second one. So they worked on some field-based biochar activated using KOH as an anodic material, in which they have removed 85% of the COD, again in a MFC, microbial fuel cell, and they have just, you see the amount, 1 milligram per centimeter square, very small amount, in which they have slowly replaced graphite with biochar. And there are series of works, I'm just giving you some essence. So what they have observed is that the internal resistance was lowered with increase in the biochar concentration. What they say is that probably due to some channeling effect during the transfer of the electrons inside the biochar material. And in another work, carbonized cotton electrodes were used and were produced using pyrolysis for other battery applications, and the electrode exhibited an energy efficiency of 73.5% and having also a good discharge capacity. Now let's move on. Another work in which the Harnetter, it's a very nice work actually. It's published in CEFIPRA-FUNDED Energy Materials in 2022. So what they did, you can see this is exfoliated biochar material, tubes. Okay. So in situ exfoliation they have carried out. They produce it from poplar catkins. Okay, and poplar is a very quickly grown tree. Okay, I think in Roorkee outside also used to grow poplar earlier. I don't know if they are living now or not. And it has a lot of uses. Now, what they used it for a zinc air battery. Now, zinc air battery is something very interesting in the sense that it has a function of a fuel cell as well as that of the battery. So, in which the zinc serves as the fuel. Okay, and you can fine tune the performance using the flow rate of the air. Okay, so that's the beauty of the zinc air battery. Okay, now still they are in the development stage in which the ORR, okay, the oxygen reduction reaction, okay, always hampers the dynamics of the cathodic systems, so that the cathodes. So what they try to do is that they try to exfoliate the graphene-like carbon nanosheets, okay, from a biochar tube. That's how this image is. Okay, you can see, and okay, it comes with carbon activation, carbonization, and nitrogen topping, and but it's a single one pot process. So that's the beauty of this particular work, published in SS Energy Materials. So they found that the GCNs have a remarkable halfway potential and very high stability. So stability issue was addressed using this exfoliation and outputting most of the nitrogen doped carbon materials. So they proposed a very simple and sustainable way, and also a less costly way or process to synthesize the nitrogen top biochar catalyst with excellent ORR properties. Right, so offering a broad potential for their application in the ZAB cathodes, that zinc air battery cathodes. So in another work, this Guwahati et al., which they published in SCS Sustainable Chemistry and Engineering, very interesting work. These are two, three works I am reporting to you, and they are all very highly appreciated works across the scientists. So what they did, they have used eucalyptus scraps to prepare the electrodes. So it's a solvent-free strategy to produce water dispersed biochar nanofibers. Okay, so it's like seeds. Okay, you can see that it's how it looks like. Okay, it's for sensing application. So you need to have seeds, right? So demonstrating the potential of this cost-effective and sustainable material in electrochemical sensing, and of course also for the fabrication of the conductive films. Okay, for this sensing again. So they did, of course, a lot of work on this, and you can read this in an interesting work. So I'll just quickly go through, because otherwise we'll run out of time. I'll not read out the methodology. Why I try to put is, to me, this is a very interesting work. So deliberately I put that if somebody is interested, some students, they can let us go through it. So what they found is that this biochar-based carbon nanofibers, sensors, exhibited a repeatable, and reproducible results. So that's the beauty of this particular work. Most of the times people say we have done 3 times averaging, but it's not so. It's not so. Okay. So we know what is the truth, right? So they have given different sets of data, and they have proved that this is not only reproducible, but it has excellent application in electroanalytical sensing, and the robustness of the exfoliated carbon has actually given beautiful results. So let me move on. Now I am going to supercapacitors. You know what supercapacitor is. So supercapacitors are a new type of energy storing devices. Okay, it's something between the traditional capacitor and the battery. It has its own pros and cons, and I mean you can read later for the students. So long cycle life, high power density, environmental friendliness, and high charge discharge efficiency is what makes them interesting candidates in the energy business, on the energy sector. So supercapacitors have emerged as a core component of the high scale or large scale energy storage systems due to their ultra high power density. So the power density is much higher than that of the batteries. They have good electrical conductivity, of course low cost compared to the traditional batteries. Physical and chemical stability is fair enough, and they have a large specific area. Again, the specific area is the term which we call SSA, specific surface area, is something directly fits to the biochar business. So as I told in the beginning that I can fine tune and tailor make a biochar having higher surface area, beautiful meso and micro pores, that I can always do it. I know these techniques how to do it. It's a matter of time, and then finalizing your process parameters so that you get a proper SSA. Right. So so if you look at this supercapacitor business, so the SSA of the specific surface area, then we need an excellent core structure. Of course, more surface area is always important. Then electrolyte choosing is also a very important factor. Okay. Now pseudocapacitance, and then of course electrical conductivity. So these are the parameters which someone should look to make a proper capacitor. supercapacitor. So there are different types of modification techniques such as active conductivity as well as the charge heteroatom and hydrogen. Okay. So we usually use the NSP, and there are many other things. Especially trying to have it in the biochar when I look especially for a this type of application, or else let us say even for a catalytic application, right? So yeah, so this is one work in which Dye et al. In a work published in again SES Applied Nanomaterials, they have fabricated carbon nanofibers from lignin. Now, lignin is something that people says that you cannot do anything with lignin. Okay, that's actually not true. Why it is so? Because lignin is very robust in structure. So breaking lignin itself is a huge energy intensive business, right? So people used to just burn it. Okay, you got lignin. Okay, so anything you do, pre-processing and all this thing. I was talking about bioethanol from bamboo. I don't need lignin. I need the cellulose. Okay, I need maybe hemicellulose also. I'll convert it to sugars. Sugars gets converted to ethanol. That's how the ethanol business, bioethanol business is. So what is happening? So another is given as a big project to me and few of my colleagues in Guwahati, IIT Guwahati, where we are doing two things. So we are basically looking after, because it will be the bioethanol will be produced from bamboo. So tons and tons of bamboos being shredded, and when you shred them, chop them, there are huge amount of the dust, bamboo dust, that's getting generated. What they will do with that? So we suggest them, why don't you make char? Because char is upcoming in a very big way. So then we presented and they gave us a big funding actually. So where we are looking after two things. One is that there are two things that is coming to their immediate attention in a bioethanol plant, is that what you will do with this dust. So dust to nahi bolunga, the bamboo dust. Okay. So we are making biochar out of that. You call green char or whatever it is. And then the lignin that is coming out of the hydrolysis system. Correct. So that also we are trying to address and convert it into some good amount of good quality of char, so that it can be used in various, because there's a big industry, they cannot just throw it or waste it. Yeah, so in this particular work, the heteroatoms, okay, content is very high. So you have oxygen, nitrogen and sulfur in good amount, which actually induced the additional active reaction sites. So that's the job of heteroatoms. I was just mentioning that heteroatoms are good, but we don't need always heteroatoms in biochars. No, we don't need it. Again, what I am going to do it, whether I am going to have a particular battery or supercapacitor application or a catalytic application, then again I can, I know which heteroatom may be good for me. I'll try to impregnate those heteroatoms. So it enhances the redox reactions and improve the wettability, thereby increasing the electrochemically active surface area. This is a low cost technology. Why? Because it is a simple flame induced oxidation method. You can see here how they are doing it in the lab scale. We can always scale it up. We don't need a big setup for all these things, because this is flame induced. Of course, they did a lot of work. And then to me this is an excellent work. So this particular method or work presents an efficient and environmentally sustainable strategy for high value utilization of the lignin. Right. Okay, so yeah, another work. I think I'll skip some of those on the with respect to the time. This is another work in which again, by Lee et al. Published in SES Sustainable Chemical Chemistry and Engineering, a derived activator carbon was used, and they have used this as a material over the anode. Okay, and they have seen then there is a 93% capacitance retention after 10,000 cycles, which is excellent. Okay, because they are very robust. Carbon nanofibers, they are very stable, they are very robust. Okay. So I'll move on. So another work in Tang et al. In applied surface science, they used sheet-egg mushrooms. Okay, so this is mushrooms. Okay, people eat it. They have produced char. Okay, fine. Anyway, it's not eatable, I think so. So they did hydrothermal treatment. Okay, and they have prepared a very nice porous carbon material, which they have used for the score capacitor application. You can see these graphs. Okay, the first one, the left hand side. So you can see there is a decrease in the specific capacitance with increasing the current density. So conforming, what it conforms? It conforms the charge storage behavior. Correct. Then if you go to the next one, the right one, it comes the middle one basically. It says it demonstrates the long-term stability of this particular capacitor. Okay, capacitance retention exceeding 90% after 10,000 cycles, which is again a very good one, right? So what they proposed is or prepared is a very sustainable electrode material for energy storage applications, offering high capacitance, excellent stability, and a favorable stability or scalability for green energy solutions. And this is another work in which they have used the MnO2 nanoseeds grown on nitrogen doped agar derived porous carbon. Agar was the material they have used. Activation, carbonization, and those steps were being used. I will not get into detail. They have also shown that how a practical, how the energy storage was successful by just lighting an LED. Okay, the back corner, this one it shows. So this work also is very nice, and it says that there is a this particular material. Okay, the MnO2 on the agar-based nitrogen topped electrode material has high energy density and stable cycle performance. Now I'm moving on to something another work. If somebody has already presented on that, then I may skip it, but just in 1 minute. So biochar in biogas production, there is a huge amount of biochar that is required. There is an issue in the biogas production. I'll show you what it actually is. So this is how the biochar gets produced. So in the traditional way, so if you put biochar into the anaerobic digester system, okay, you get rid of the H2S and the ammonia that's coming out. Okay, so you do not have to go for more purified, more purifying steps. Okay, so this is more in detail. So I'll skip all these things. Then we have biochar in air purifiers. Okay, we know how it works for the global climate change. We have lot of to do with carbon dioxide sequestration and capture. And again, I'll skip what I wanted to show. Is that what we are doing? So just allow me. There are a lot of this one. These people have sought. I just talked to Sonal that people have already talked on these things. Yeah, I just wanted to show what we are doing. Okay, another 2 minutes. So one of my students, PKS, he's working on 5 HMF production, hydroxymethyl perfluoride. What it is? So it's a platform chemical actually. It's an intermediate compound that can be further converted into variety of chemicals, fuels and materials. Since my group is by group person fuels, so we are more interested in the fuel business with the HMF. So we have lot of biomass that we have actually screened for making HMF using a power reactor. This is a high pressure, high temperature reactor, in which what we have done. Now in a simple nutshell, we have used a bamboo, which is a soft grown bamboo. It's called mula bamboo in a local Assamese language. So, sorry, muli bamboo. It looks like radish. Okay, so that's what, right? So in that thin, not it doesn't look like radish. Okay, so in the appearance. So we have used this bamboo biomass for 2 things. We have prepared a bifunctional catalyst using this bamboo. Okay. And biomass, again use that same biomass and the same bamboo based catalyst, okay, for preparing IPHL. Right, I'll show you how it is. So this is the process parameter optimization during the biochar production. I'll skip it. I will show what HMF is been doing. So you can look at this. When we produce HMF using the hydrothermal liquefaction technology, I do also produce levulinic acid and formic acid. Now, again, levulinic acid, La, which we call, is an excellent intermediate, platform chemical again. So what we are focusing right now is that in a single shot, when I am doing hydrothermal liquefaction, how do I optimize both? Right. Now, when I say I am producing 5 HMF and I am getting La and Fa, I will not throw La and Fa, right? Okay, I can skip Fa because it's not a very costly or material, but La is, okay. So now we are trying to, you can see that yield is only 25%. There are some of the words which are not reported, so I am not showing you in details. So right now we are doing the process optimization of the hydrothermal liquefaction technology, in which we are targeting 5 HMF as well as La. How can we have both, or how can we increase the yield of both these products? So in another work, Abhishek, he is a PMRF fellow. He started working or preparing, again, Bambusa tulda is another variety of what is that is called bamboo for preparing electrodes, okay, for the battery and supercapacitor application. So I'll just say that you can see that this particular CV is not in rectangular nature. Yeah. There are issues with that, and because it improves the redox reactions from surface functional groups, and the presence of these energy-rich functional groups in the biomass-derived carbon can contribute to pseudo-capacitance. So that's why the nature of the CV is something like this. Okay. So I'll just wind up by saying 50% of my group work on algae. Okay. So we produced different types of varieties of the biofuels from algae, and when you extract this one oil, so the biomass that left out, we again converted to hydrothermal carbonization and got the hydrochar. Now this hydrochar is the benign hydrochar which I was talking about. I think I should stop. Our guests have arrived, so we'll proceed with the validation. And this is in another work in which that microalgae biomass, in which the oil has been removed, is being converted into a catalyst. Again, use it in the same transesterification reaction. So for us in my group, there is nothing waste. We always do in the recycle. So I think I'll stop here. We all know that biochar has a lot of applications, right? Starting from your soil amendment, which people have talked about earlier, and what I have covered is happening right last 5 to 10 years is the use in the batteries and supercapacitors, and then of course biogas and the catalyst. So there is a huge market of biochar. So let us work together to tap that potential and make a good and use of the biochar in a more greener way. So thank you very much for giving me the opportunity. I would like to say thanks to Dr. Sonal, our host, for his gracious invitation and hosting us in a very nice way. So we can give him a big round of applause. And
Long live India and France friendship.